Welcome to a new physics lesson. Today we'll continue with the chapter on electromagnetic induction. Okay, so basically we have the magnetic flux. The formula given in the booklet. The magnetic field times the area times the cosine of the angle made by the magnetic field with the normal to the area. So this is the area. The normal is a line perpendicular to the surface area. The magnetic field is a vector in whatever direction, and this is the angle theta in between the normal to the surface and the magnetic field. And the induced voltage E is negative delta phi over delta t. Okay, so the variation of the magnetic flux divided by the change in time, and I have a minus sign here to remind me of Lenz's law that says that the induced voltage generates an induced current that opposes whatever has caused the change in magnetic flux. And if I have n loops, of course, n loops of wire, the formula becomes E equals negative n delta phi over delta t. Okay. Now, what can make the magnetic flux change? What can make the magnetic flux change? Well, it could be a change in the area, A, which gives me an induced voltage BVL, as we have derived last week, or maybe a change in the angle theta, which is how electric generators work. This is how electric generators work. And we'll look into more details later on. Or a change in the magnetic field B. And this basically means that the magnet goes in and out of the coil. Okay. It would seem that there aren't many formulas that apply to this situation. Uh, However, surprisingly, this year in May, there was a problem on the higher level exam with exactly this situation. And I want to go over this problem right now to understand better what happens. So let's look at the problem. A fixed horizontal coil is connected to an ideal voltmeter. A bar magnet is released from rest so that it falls vertically through the coil along the central axis of the coil. Okay, so the magnet first approaches the coil, then enters the coil, then exits the coil and falls farther away. The variation with time t of the electromotive force induced in the coil is shown. Induced EMF in millivolts as a function of time. What are the units for time? We have no units for time. Okay. Question number A, part 1. Write down the maximum magnitude of the rate of change of flux linked with the coil. So problem number 8, higher level, paper 2, May 2022. Okay. Flux linked with the coil, flux linkage is N times the magnetic flux in one coil, one loop of wire. Okay, N loops of wire in the coil. Okay. And what is the rate of change? The rate of change of flux linkage. It is N times delta phi over delta t. Well, This, according to Faraday's law, Faraday's law, okay, E is negative n delta phi over delta t. So this gives me the induced voltage, but I want I want magnitude, the magnitude of this rate of change of flux linkage. The magnitude, I take the absolute value of E is equal to absolute value of negative n delta phi over delta t, yeah? So, and I want the maximum value of this, maximum value of the magnitude of the induced voltage. So now I have to look at the graph. From the graph, this is, and let's take a look at the graph. Okay, so this is the EMF E, and I want the maximum value of the absolute value of this. Well, here I have 3 millivolts, yeah? Max E is 3 millivolts. Minimum E is negative 5 millivolts. The minimum value is negative 5 millivolts. But because I have to take the magnitude, the absolute value of this, the answer is 5 millivolts. Okay, 5.0 millivolts from the graph. Okay, because I have to take the absolute value. Okay. So the EMF E goes from negative 5 to 3, but the absolute value of E, the magnitude of E, goes from 0 to 5. 5 is the maximum. Okay. That was easy. This is the max value of absolute value of E. Okay. Next question. So we got 1 mark point. Next question. State the fundamental SI unit for your answer to A part 1. Okay. The EMF, which is a voltage, is measured in volts. Okay, but this is not good. The SI unit for voltage is the volt. That's not the question. The question is what is the fundamental SI unit? Fundamental. What is the fundamental SI unit for voltage? Okay, here we have to understand the difference between SI unit and fundamental SI unit. What are the fundamental SI units? The fundamental SI units. Okay, the meter, the second, the kilogram, the ampere, okay, the mole, the candela, we don't need those. Okay, so basically we need to express 1 volt in terms of meters, seconds, kilograms, amps. Now remember, the amp is the fundamental SI unit, not the coulomb, because electric currents can be measured based on the magnetic force between parallel wires with the electric currents in them. The electric charge of the electron, of the proton, those were measured much later, and by that time the fundamental SI unit was the amp, and things were left this way. Okay, so how do we do this conversion? Volt, what's the volt? Well, remember the voltage, yeah, is the change in electric potential okay, which is the change in electric potential energy over the electric charge of the particle that goes from one place to another. Okay, and voltage is measured in volts, energy is measured in joules, electric charge is measured in coulombs. Okay, so that gives us a relation, yeah? 1 volt is equal to 1 joule over 1 coulomb, but the coulomb is not a fundamental SI unit. So now we rely on another formula. The electric current is the electric charge that flows through a wire in a time, delta Q over delta T. The electric current is measured in amps, the charge in coulombs, the time in seconds, okay, which means that 1 amp is 1 coulomb over 1 second. Okay, which means that 1 coulomb is 1 amp times 1 second. And we could substitute these fundamental units in here. Yeah? Both the amp and the second are fundamental SI units. Now, what do we do about the joule? Okay, to figure out the units for the joule, I'm gonna write down the formula for kinetic energy. Kinetic energy is 1/2 the mass times the speed squared. So energy is measured in joules. The mass is measured in kilograms, and the speed is measured in meters per second. Okay, but I have to square this. So in conclusion, 1 joule is equal to 1 kilogram times 1 meter squared over 1 second squared. And this value of the joule, okay, will be substituted here. Okay, now we are ready to find the answer. So 1 volt is equal to, let's see, forget about the 1, just volt. Okay. Kilogram meter squared over second squared over amp times second. This is kilogram meter squared over amp second to the third power. Okay, which in IB style is written kilogram meter to the second, amp to the negative first, second to the negative third. And this is the correct answer. For which you get another mark point. Okay. Explain why the graph becomes negative. Well, this is the thing. When the magnet is above the coil, the magnetic field is increasing. the magnetic field lines go from the North Pole to the South Pole. So in this case, the magnetic field lines will look like this. Okay. And when the magnet is above the coil, and getting closer, the magnetic field is increasing. The magnetic field is the magnetic flux density. That's the number of field lines that cross the surface of the coil that is getting bigger. When the magnet is below the coil, and getting farther away, the magnetic field is decreasing. Okay, so okay. Please notice that in both situations, the field lines are going down, okay, here. So the magnetic field is going down in throughout the whole experiment. Um, so if we graph the magnetic field as a function of this y coordinate going down. Okay, what we'll see very, very far away. Very, very far away, the magnetic field is 0. And then as the magnet gets closer, the magnetic field increases. Okay, reaches a maximum value and then decreases. Okay. Okay, so B is 0, very far, when the magnet is very far. The magnetic field in the coil, yeah, is 0 when the magnet is very far. Same thing here. Okay, and then there is a maximum value right here, yeah? So magnet is getting closer, okay? And then I reach a maximum value, and at this moment, the magnet is right inside the coil. The magnet is in the center of the coil. The magnet is in the center of the coil. Okay. Okay, so here it is above the coil, and here it is below the coil. Moving away. And if we take the derivative of this, okay, we can find the EMF, the induced voltage. Okay, so the magnetic flux is the area of the circular loop of wire times the number of loops times the magnetic field, yeah, pi r squared, yeah, number of loops. Okay, and the EMF is negative delta phi over delta t, okay, and this is proportional to delta B over delta T, the change in magnetic field over the change in time, because the area of the circle is constant, the number of loops of wire in the coil is constant. Okay, the only thing that changes is the magnetic field in the coil. In the coil. Okay, now if we look at this graph, we can quite easily calculate the derivative, the change in B over change in time. Okay. At the beginning, that's 0. And then okay. And then at this point, when the magnet is in the center of the coil, it is again 0. Because the derivative delta B over delta T is the slope of the tangent line, yeah? And the tangent line right here at the maximum is a horizontal line, okay? And slope of tangent is 0 here, yeah? Slope of tangent line is 0. Okay, here at the maximum. So, but throughout this section, the slope increases and then decreases. So we'll see this behavior 0, and then it goes up, and then it goes down. Okay, and here the magnetic field decreases, the derivative is negative. But again, very, very far away, the derivative becomes 0. So it's negative, and then the graph turns around, and okay, I end up with a 0 EMF. Okay, when the magnet is very, very far away, there's no induced EMF. Okay, and this is the graph, of course, as a function of Y. Well, that's the reason why the induced voltage has a positive peak and then a negative trough. The sign, okay, the sign is meaningless unless I show how the voltmeter is connected. Okay, if I swap the black and red leads of the voltmeter, the voltage measured changes sign. Okay, so we don't focus on the sign, and that's the explanation. So one more time, let's read the question so we give a clear answer. Explain why the graph becomes negative. Yeah. So when the magnet is above the coil and getting closer, the magnetic field is increasing. When the magnet is below the coil and getting farther away, the magnetic field is decreasing. Okay. Same thing with the magnetic flux. And when the magnet okay, when the magnet is in the center of the coil, the magnetic field, and therefore the magnetic flux, reaches a maximum. Okay, the maximum means the derivative is 0. The derivative is 0 at a maximum. That means the induced EMF is 0 when the magnet is in the center of the coil. Okay. You have to write this down. This is in the mark scheme. The induced EMF is 0 when the magnet is in the center of the coil. And at this moment, the EMF becomes negative. The EMF changes sign. Okay. If it was positive, it becomes negative. If it was negative, it becomes positive, okay? And again, it depends on how I hook up the voltmeter. Depending on how I connect, depending on how I connect the voltmeter. Okay. Next part of the question. Part of the graph is above the time axis and part is below. Outline why the areas between the time axis and the curve for these two parts are likely to be the same. Well, time to look at our graphs. Okay. And the question is why the area above is equal to the area below the time axis. Well, here I graph the y coordinate, but because the y is a monotone function of time, okay, same thing. Actually, I need to graph it as a function of time. These are not the areas I worry about. Okay. So another graph with the magnetic flux as a function of time. Okay. That was proportional to the magnetic field. So 0, and then goes up, reaches a maximum and decreases to 0 when the magnet is very, very far away. Okay, a maximum value, let's call it phi max. Okay, this is the time when the magnetic coil, when the magnet is in the coil. And if I represent the derivative, the variation of the magnetic flux over time as a function of time. Okay, 0, and then here again 0, so goes up, goes down, and then it goes down, and then it goes up again, and far away from the coil again, there's no EMF induced. Okay, and the question is about these areas. Okay, why are these areas equal? Okay, and the reasoning is because here we have a derivative, yeah, d phi over dt, and according to Newton's theorem, yeah, area 1 is the magnetic flux here minus the magnetic flux here at negative infinity. Okay, but the flux at negative infinity is 0. Okay, so this doesn't matter. And area 2 is the magnetic flux here minus the magnetic flux here. The magnetic flux at positive infinity minus the magnetic flux when the magnet is in the coil. And again, this is 0, doesn't matter. And what do we notice? In absolute value, absolute value of area 2 is equal to area 1. Of course, this is negative because it's an area below the time axis, below the axis. And this is positive. It's a positive area because it is above the axis, above the time axis. And that's the explanation. Same thing happens. Okay, whenever we integrate other functions. So if I have a derivative on the vertical axis, then the area is the change in that function that I derivate. Yeah, for example, if I represent the force, which is the derivative of momentum with respect to time, okay, as a function of time, okay, what is the area? What is the area? The area is the impulse, okay, which is the final momentum minus the initial momentum, yeah? The change in whatever quantity I derivate here. Okay, very important theorem, Newton's theorem that helps us understand integration and derivation. So same thing here, but the function was the derivative of the magnetic flux. Okay, this is the maximum value here. This is yeah, what I call phi at the time t coil. Okay, good. Back to the question. Predict the changes to the graph when the magnet is dropped from a lower height above the coil. What happens with the graph when the magnet is dropped from a lower height? Okay, well, lower height means lower gravitational potential energy. That means lower kinetic energy. That means lower speed. Okay. And for this statement, you get one mark point. Magnet moves slower. Okay. Now, because the magnet moves slower, because the magnet moves slower, the interaction time will be larger. Okay. So okay. If initially I had something like this, now I will have something like this. Okay. Um, okay. And of course, so bigger height, okay, and the lower height. Okay, the magnet is dropped from a bigger height. The magnet is dropped from a lower height, yeah. And there are two different time scales. I overlapped one graph over another. Of course, the time at which the magnet is in the center changes too. And what do we notice? That the peaks will be smaller, yeah? The peaks will be smaller, okay? Because the areas must remain the same, yeah? Because the areas 1 and 2 must remain the same, okay? Both are equal to the maximum magnetic flux. This conclusion does not change. The conclusion we reached previously. So the areas, yeah, are still equal to the same number, but because the interaction time is bigger, the graph is wider, but also the peaks are smaller, yeah, to make sure that the areas stay the same. All four areas are equal to the same thing. Okay, the peaks will be smaller because the areas 1 and 2 must remain the same, equal to phi max as before. And that's how you get the 3 mark points for this problem. Okay. Now we are ready to look at the third situation, in which the angle changes. Okay, and this is part of chapter 11, section 2, power generation and transmission. Okay. In this situation in which theta changes, right? The angle between the loop of wire and the magnetic field changes. This situation comes with a lot of formulas in the booklet. Look at all these formulas here. I RMS equals I0 over square root of 2. V RMS, RMS stands for root mean square, is V0 over square root of 2. R is equal to V0 over I0. P max I0 V0. Average power 1/2 I0 V0. Okay. And the last formula, that's something else that relates to transformers. That relates to transformers. So let's see what's going on with these formulas. Okay, first of all, this is AC electric power generation, yeah? Okay, the transmission, that's when we'll meet the transformers. But right now we focus on AC electric power generation, yeah? And what do we have? We have, okay, for simplicity, let's use a horseshoe magnet. Okay, north, south. Okay, field lines from north to south. And here, inside the magnet, I have the coil that rotates. And of course, I also need some special electric contacts to make sure the wires don't twist and break, right? These are the electric brushes, okay, which we probably see in the textbook. Yes. Okay, so these are the brushes, okay, some slip rings, and this allows the coil, the loop of wire to rotate, okay, without having the connections twist and break. Okay, now of course after a while these electric contacts at the brushes wear off, and you have to replace them. And this problem shows up in electric generators and also in electric motors. Like for example, an electric drill. And I remember I replaced the brushes in a DeWalt drill after many years of use, and you know, it worked like new after. Okay, so back to the formulas. The magnetic flux and okay, BA cos, okay, BA cos theta, and the EMF negative N. Okay, and here I'm, instead of delta phi over delta T, I'm gonna write d phi over dt. This is what we want to be mathematically accurate, the derivative. The derivative. And what is the derivative of the cosine function? D over d theta. Okay. Let's not rush. Theta, first of all, okay, changes with time. Okay. Exactly like we discussed for circular motion, yeah? Circular motion. Okay, theta is what? Omega t plus theta 0. Okay, it changes uniformly. Omega is the angular velocity. Angular velocity. Okay, omega is change in theta over change in time, the derivative. Basically, you can see that if you take the derivative of this function, you get omega. Okay, so now we can calculate the derivative of cosine theta over the, okay, as a function of time, d cosine theta over dt. I used the chain rule, yeah? The chain rule from calculus. And I get d cosine theta over d theta times d theta over dt. The derivative of the cosine is the negative sine of theta. D theta over dt is omega, yeah? So this gives me the derivative I need for the EMF. Okay. So one more time. The EMF is negative n. I take the derivative, okay. B is constant, A is constant. The derivative of the cosine is negative sine of theta times omega, okay? And in conclusion, the EMF is a maximum value times the sine of the angle, okay? Where maximum value of induced voltage, right, V0 is what? The number of loops of wire in the coil times the magnetic field of the horseshoe magnet times the area of one loop of wire times the angular velocity. The higher, the faster I spin the coil, the higher the maximum voltage. Okay. So now let's visualize this AC generator connected to a resistor. Okay. The voltage on the resistor, as we've seen, is V0 sine of theta. What is the electric current in the resistor? By Ohm's law, the electric current is the voltage over the resistance. Okay, so this will be V0 over R sine of theta, which is I0 sine of theta. The maximum value of the current I0 is by definition V0 over R. These are the I0 and V0 from the booklet. Okay. And see this equation, R is equal to V0 over I0. This is Ohm's law. This is exactly what we have written. Okay, but now the question is, what is the electric power that turns into heat in the resistor? Okay, this is the so-called Joule heating, Joule effect. What is the electric power that turns into heat in the resistor? Well, we know that power is voltage times current, P equals IV, but the voltage and the current are changing in time. Okay. And okay, basically the electric power, P is IV. It is I0 V0 sine squared of theta. I get a sine from the current and another sine from the voltage. I0 V0, this is what I call the maximum power. As you can tell, the maximum value of sine squared is 1. Okay, and when sine squared reaches its maximum value, okay, the maximum power P max is I0 V0, which is this formula right here from the booklet. Okay, but now I want to find out not the maximum power, I want to find the average power. The average power. That means, okay, I replace the AC generator with a DC generator. Okay. AC, remember, stands for alternating current. Okay, so I get that graph, the sine wave, yeah? And DC stands for direct current. Okay, which means the current is constant. Okay, so I replace the AC generator with the DC generator. That gives a constant voltage VRMS and a constant current IRMS. And of course, by Ohm's law, R, the resistance is VRMS over IRMS, which is the formula we see here. And now I want to figure out what value of VRMS will produce the same heat in the resistor. What value of VRMS will produce the same amount of heat in the resistor? Okay. And I will look at one period. Yeah, I only have to consider one period. Time, power, okay. The power will be I0 V0 sine squared of omega t. Okay. Technically speaking, I have theta 0 here, but I can make it 0 by choosing the origin on the time axis. By choosing the origin on the time axis. Okay. And sine squared is always positive, okay? And the graph will look like this. Okay. Here I have the period, yeah, which is 2 pi over omega, because omega is 2 pi over the period. Okay, and here, this is the period over 2. Okay. So I could, right, I could also represent the current and the voltage, the current is a function of time, yeah. And the voltage is a function of time. And of course, negative times negative gives me positive. This is why the power is always positive. And what is the heat produced? What's the electric energy dissipated? Well, the area here is the electric energy dissipated, yeah? Okay, constant power, energy dissipated E is equal to power times time, yeah? And variable P, variable power, okay, energy dissipated is area under graph. Because here, right, when I multiply the power by the change in time, delta T, okay, I get the area, correct? If I represent the power as a function of time, and it is constant, then this area under the graph is the energy dissipated, yeah? From here to here, I have the power. From here to here, I have the change in time. Okay, I go from an initial time to a final time. Okay. So the energy dissipated is the area of this rectangle. And when the power is variable, I simply split this total area into a lot of very, very thin, yeah, rectangles, and I add up the areas of all these very, very thin rectangles. That gives me the total area, which is equal to the total dissipated energy. And this is how we'll figure out the value of the constant voltage that produces the same amount of heat in the resistor. We'll leave this for next time because the class is almost over. Just a moment to give the homework assignment. So homework, what's the homework? Read chapter 11, section 2, power generation and transmission. Okay, and go over the worked examples. Okay, I think this is enough for today. Thank you very much for your attention and good luck.